Hey guys, in this video we're going to take a look at the foundations of how an electric motor works because it's the most common application of magnetic force on current carrying wires. So let's get into it. Alright, so here I have a magnetic source. This could be a horseshoe or any other kind of magnet, as long as I have a uniform constant magnetic field running, and let's just say here in our example from left to right. And then in between the north and south poles of this magnet, I have a current loop, is what we'll call this. Now it's a piece of copper wire in this case that is shaped into kind of a square or rectangle shape, and it has these two descending and ascending portions at the bottom. That's where it will attach to some sort of power supply. There is this piece at the top here, which is kind of its anchor point, and that's its axis of rotation. So you can imagine this little loop of wire spinning around this axis of rotation. And this is basically an electric motor, right? It takes electric potential energy and this energy from the magnetic field, and it converts it into kinetic energy. So that's what we're going to be focusing on, is how does it do that? How does it create this turning or spinning motion? So we're going to take a top view, which is the easiest way to analyze the situation. So here I see the magnetic field running left to right, and then I'm going to set it at this orientation where the loop of wire, the top of it, so if you imagine looking from the very top, it runs exactly parallel with the magnetic field line. Now, if we think about our right-hand rule, and we're going to kind of toggle back and forth between this side view or this perspective view and this top view. Now, if we use our right-hand rule and we think of the direction of the current, so I'm going to put a direction of current through this loop, and we're going to remember use our index finger as the current, and the magnetic field is our three other fingers. So I'm going to point the current, and in this portion of the wire, the current is pointing up, all right? And the magnetic field is pointing to the right, which leaves the force pointing into the page, or kind of pushing backwards in the perspective drawing. Now, if I draw this from the top view, I see that the current is running into or out of, I guess in this case, out of the screen. And that is exactly 90 degrees to the magnetic field line, which leaves the force pointing up in this case, or up along the plane of the screen. Now, if we focus on the other side of the loop, we see that the current here at this portion is facing down, and the field still pointing to the right. And so I see that the force is actually pointing in the opposite direction of the force that was acting on the other side. So in the top view, I see that the current's going into the page, or into the screen, and my magnetic field is pointing to the right, and so my force ends up pointing down towards the bottom of the screen, or along the plane of the screen. So we see here this very cool drawing, and with a good knowledge of torque, we can understand that if this axis of rotation here in the middle is the place that it's turning around, then if I push up the screen on the left and down the screen on the right, I've created this spinning motion. Now you might be thinking, well, what about the top and the bottom? So the width of the loop, for instance. Well, you can see that the current at that point and at the bottom point, they are actually parallel with the magnetic field at all times. And so they don't experience a magnetic force whatsoever. So the Lorentz force is only acting on the vertical portions of the loop. And by doing that, it creates this push. So we can see that whatever turning point it's at within the magnetic field, so here we're looking at the top view, is that the force is always going to be perpendicular to both the current and the magnetic field using that right-hand rule, right? So that Lorentz force always points at a right angle. Now the torque is going to change. So let's just recall that the Lorentz force here is equal to ILB, or in this case, we would call that current times length times magnetic field. And the length is this length, or the, in this perspective, drawing the height of that loop of wire. And we know the torque equation, one of them at least, is that torque is equal to F cross R. And remember, F cross R in this case is F R sine theta. Now, R is the distance from the axis of rotation to where the force is applied. And then, of course, theta is the angle between that position vector and the force vector. So if we do our torque equation here, let's say for this, the first example where the force is exactly 90 degrees, we see that the distance from the axis of rotation to the edge where the force is applied is the width divided by 2. So we do W divided by 2 times F times the sine of 90 degrees. And then we've also got to add on the other side. And both of these you can see are pushing clockwise, so they're both positive. So I would do that again. So I'd have width over 2 F sine theta plus width over 2 F sine theta gives me width F sine theta. Now what's really neat is that you can see that the torque value is changing slightly, right? So it's at its greatest in this configuration. Remember, we're looking here in the top view. And then in this configuration, when the loop face is pointing the same direction as the magnetic field, right? So you can think of that area vector as pointing in the same direction as the magnetic field. There is no torque because the force is at 0 degrees with the axis of rotation. And then you see once it makes its full rotation, or it's getting into its next rotation, the torque flips direction, which is kind of neat. So the force on each side has now flipped direction. So if we substitute in the ILB force into the torque equation, we see that we have width times ILB sine theta. So that's the expression that combines the Lorentz force, or the magnetic force, with the torque. Now we can do one more simplification, which is kind of neat. Width times length, which here in the side view would be the area of this loop of wire. And so it turns out to be that torque is equal to IAB sine theta. So the area actually does have an effect. The area of this loop does have an effect on the torque, or a way you could think of it is the spinability, or the how well this loop turns in the magnetic field. And then to add to that, if you just multiply, if you have multiple turns of wire, so multiple loops of wire, then you just multiply that by a factor of n, because that will be each amount of force multiplied over the strength of the magnetic field. Now, if you're burned out and you just want to move along, that's fine. This last little section here is just going to kind of point to consideration a few kind of neat things. So for the eagle-eyed among you, you may have noticed that when the torque direction changes, wouldn't that just mean that the loop would oscillate back and forth, right, between those two positions, because the force is going to keep rotating? Unless we reverse the current in the loop, that is going to happen. So we have something called these little automatic switches, basically, which flip the direction of the current, like I'm showing in this picture. We call these brushes. And the brushes help to just flip the direction of the current, and that way it will keep the loop spinning in the same clockwise direction continuously without flipping back and forth. The other cool application is a meter, which basically has a pointer or a gauge mark that is attached to the rotating axle here on the motor. And what you can see is that when the current value changes, so there's some other sensor that basically adjusts the current value, then that will allow the loop to turn a certain amount before the current cuts off, and the coil will stay at this designated position on a scale, and that will kind of show a specific value. The meters are very similar, but they're only actually going to rotate through a part of a revolution. The magnetic poles of this meter are shaped in this kind of curved pattern, and so that they can keep the component of B perpendicular to the loop constant, so that the torque does not depend on the angle, and the deflection against the return of the spring is proportional only to the current. So to end this little video, I'm going to leave you a little challenge here. So here's a really cool little snippet video of what we call a homopolar motor. And we've got this copper wire here placed, shaped first, and then placed on a battery with a magnet on the bottom. And the bottom of the wire is able to conduct a current through this wire. And what we see happen is that when we place the wire on top of the battery, it spins. So the challenge is for you to figure out how this is happening. So the next section of this course on magnetism switches to answering the question, why does the magnetic force only act on moving charged particles or current carrying wires? Because so far we've described that it's happening and what's happening, but we haven't really figured out why it only acts. So I hope to see you back for that little stretch of series of videos coming up.